When you think about it, modern medical implants are just incredible. We've got joint replacements that get us walking again, pacemakers that keep our hearts ticking. We've figured out how to fix and replace parts of ourselves in ways that are honestly miraculous. But there's a catch. There's this fundamental conflict that happens deep inside our own bodies. So let's get right into it. What happens? You put this amazing, sophisticated piece of engineering into a person, and you expect it to just work. But our bodies, well, they have an immune system that's been perfected over millions of years, and it often looks at that implant and just sees an invader. So what happens when our own defenses turn against the very things that are supposed to heal us? All right, so to really get this, we have to go back to a basic rule of biology. Your body has this incredibly sophisticated security system. Its number one job? Telling the difference between self and non-self. It's on a constant 24/7 patrol for anything that doesn't belong. And that security system's response has a name, and it's the key idea for this whole explainer, the foreign body response, or FBR. It's the technical term for how the body reacts to any material it doesn't recognize as its own. And this isn't a mistake, it's not a bug in the system. It's a powerful, ancient defense mechanism, and its goal is simple: contain or destroy the foreigner. So the moment an implant goes in, the FBR kicks into high gear. And you should think of it like a multi-stage security protocol. It doesn't just happen all at once. It's this coordinated, escalating cascade of events happening at a cellular level. It's a fight. What's so fascinating is how methodical this attack is. It starts literally the second the implant makes contact with your blood. That's phase one. Proteins in your blood just instantly glom onto its surface, basically tagging it and screaming, "Hey, something new is here." That tag triggers phase two, acute inflammation, where the first responder immune cells rush to the scene. Then it gets more serious with phase three, chronic inflammation. The heavy hitters, cells called macrophages, show up. Now, they can't eat a big metal or plastic implant, so they move to phase four. They start fusing together, forming these massive foreign body giant cells to try and overwhelm it. And finally, in phase five, the body almost gives up trying to destroy it, and instead tries to wall it off completely by building a thick, fibrous scar tissue capsule around it. And during this whole process, especially in that chronic phase, the area right at the implant's surface is a war zone. The immune cells are releasing this nasty cocktail of digestive enzymes, super reactive oxygen molecules, even acid. So the key takeaway here is the body isn't just passively accepting the implant. Oh no, it is actively creating a hostile, corrosive environment, trying with everything it has to literally dissolve and destroy this foreign object. Now, this battle I'm describing, it isn't just some abstract theory. Let's look at a real-world story from a research lab that was working on a scaffold to help regenerate damaged nerves. It's the perfect example of this challenge in action. In the lab, in a petri dish, the results were just beautiful. The team had designed this scaffold with these tiny, microscopic grooves, and they worked perfectly. The grooves guided the nerve cells, getting them to grow in a nice, straight, organized way. I mean, the project was looking like a huge success. But then they moved from the lab into a living body, and everything went wrong. The foreign body response completely took over. Those same nanoscale grooves that were designed to guide the nerve cells, well, they turned out to be the perfect handholds for immune cells to grab onto. So instead of nerve growth, what they saw was an absolute swarm of macrophages and giant cells clogging up all the channels and then wrapping the whole thing in that fibrous capsule. The nerve growth was completely blocked. What worked perfectly in the lab failed spectacularly in the body. And this just nails the problem, doesn't it? The researchers did an amazing job designing their material to talk to nerve cells, but they kind of forgot about the body's security force, the immune system. The very feature that made the design so clever for its intended purpose also made it a giant flashing target for the FBR. And this experience, which happens all the time in this field, by the way, has forced everyone to take a step back and rethink a really fundamental idea. What does it actually mean for a material to be biocompatible, to be friendly to the body? For a long, long time, biocompatibility was basically just a do not list. A material was considered good if it was non-toxic, if it didn't cause irritation, if it didn't cause cancer, and on and on. The whole philosophy was just the best implant is an invisible implant, one that the body just ignores. The goal was to be as inert, as passive, as boring as possible. Just sit there and don't cause any trouble. But that nerve scaffold story shows us that do no harm just isn't enough anymore, especially if you want to do cool things like regenerate tissue. And this has led to a massive paradigm shift. The new goal isn't just inertness, it's biointegration. It's not about being ignored by the body, it's about actively communicating with it. The goal has shifted from just do no harm to actively do good, from playing a passive role to an active, guiding role in healing. Now, let's be totally clear. That old philosophy of being inert gave us some incredible successes. I mean, materials like titanium alloys in your dental implants, PEEK in spinal cages, silicons, these are the workhorses of modern medicine for a reason. They are so stable and they provoke such a minimal response from the body. They work because for those jobs, a quiet, passive presence is exactly what you need.
But for the next generation of medicine, for true regenerative therapies, we need our materials to do more. We need them to be active players in the healing game.
So this creates a whole new job description for biomaterials. They can't just sit there anymore. They need to be designed to encourage the right kind of cells to grow. They need to help send the right molecular and mechanical signals that tell cells what to do and where to go. Really, the ultimate goal is to optimize how our bodies regenerate tissue by working with our biology, not just trying to hide from it. So really, the grand challenge for the future isn't just about being clever and hiding from the foreign body response anymore. It's about engineering materials that are so smart they can actually speak the body's native language, the language of proteins and cells and signals, so they can actively guide the whole process of healing and regeneration. And that leaves us with a pretty exciting question to think about, right? Once we actually master this biological conversation, and we can create materials that are true partners with our bodies, the possibilities are just mind-boggling. What will we be able to repair, to rebuild, to regenerate next?